Hello everyone. Today we will start with BPSK. Before jumping to BPSK, we should know what is PSK. It will be better if you watch my ASK videos. You will get the link in the description. So, in ASK, we were playing around with the amplitude of the carrier wave according to the message signal. Here, as the name itself suggests, we are going to play with the phase of the carrier signal. If I talk about more general definition of PSK, it goes like this. Firstly, it is a digital modulation scheme where our data or message signal is processed, and it is processed by changing the phase of a constant frequency signal. And this constant frequency signal is our carrier signal. This PSK is a general case. That means it has many classification, and its classification is based on its number of phases. For instance, there is BPSK, binary phase shift keying, in which our mapped incoming data symbols, that is our bits 0 and 1, are given two possibilities, that is 0 or pi. If I talk about this is the BPSK, this is QPSK. Here we have the 4 combination, that is 45 degrees, 135 degrees, 225 degrees, and 315 degrees. And we can go on making different combinations. Today we will understand this binary phase shift keying. Okay, this is my waveform. Before jumping to waveform, we should know following things. First thing is that our message signal B of t is represented as NRZ form, but the NRZ form is polar. That means we have two polarities. In unipolar, we used to have only one pole, that is like this, but in polar form we have both negative as well as positive. Here, if we have bit 1, then we will have a positive volt, and when we have bit 0, then we will have a negative volt. For simplicity, I am taking these voltage levels as 1. We can take any values depending upon our system. Now, with this, we will understand this is my message signal. For bit 1, we are supplying a positive voltage, and for bit 0, we are supplying a negative voltage. This is our high frequency carrier wave, and see, for logic 1, we have a 0 phase shift. That is, for bit 1, we have a phase of 0 degree, and for bit 0, we have a phase of 180 degree. That means here we encounter bit 0. This is 1. Here we encounter bit 0. So we can see how there is a shift in phase of this carrier signal. And if I give a lame definition of phase, it is the starting point of wave. So here we can see starting point of wave is changed. How much change? 180 degree shift is there. So here we can see, and here we can see how they are changing their phase. We can see there we are not disturbing either frequency or the amplitude of the carrier signal. If I write the equation of this, it is simply S of t is B of t into C of t, that is A into cos 2 pi fct into B of t. For bit 1, we have B of t as equal to 1 volt. Here we have taken as an example of 1 volt for simple calculation. This is just a constant. You can take any value depending upon your system. So we get this A into cos 2 pi fct. For bit 0, we have B of t as negative 1 volts, right? We will put negative 1 volt. We will get S of t, and here S of t as minus A into cos 2 pi fct. And we know cos 180 degree plus theta is minus cos theta. Hence we can write this equation as A into cos 2 pi fct plus phase, that is 180 degree. Here we can see. To get the bandwidth information, we should use the Fourier transform over our PSK signal to get bandwidth information. So if I do the Fourier transform of this, then this will simply be A by 2 B f minus fc plus B of f plus fc. Let us plot this signal. We know that B of t is our rectangular pulse, right? For 1 volt, 1 bit, we have a positive peak, that is this, and for negative we have this. So there is just simply a change in the amplitude. We are not disturbing our bit time period and other quantities. Hence this Fourier transform is a rectangular Fourier transform is a sinc pulse, and here there will be a just reverse of this. Hence if we take the Fourier transform of our original equation, we will get this, and we will have two sinc pulse present, one at minus fc and other at plus fc. Let us plot here, and this all I have done in the ASK video. You can see for more understanding. We will have one sinc pulse here, another at here, minus fc and plus fc. we have our bit time period as TB. Therefore, our bit rate will be RB, that is 1 by TB. Hence, we will have this TB. To get the bandwidth information, we take this positive part. This minus this will give us bandwidth, and that will be 2 by TB, or 1 upon TB can be written as bitrate 2RB. Therefore, we can see the bandwidth requirement is double in BPSK.